Good morning all. Summer's fast approaching and I've been thinking about my PWM5 Solar Charge Controller. That's the surface mount version. It's just 1/2 inch by 1.1 inches. In fact, I'm going to bring in the one from outside. Let's take a look at how that has fared. It's been out there for several months. And here it is, and it is showing signs of corrosion. I'm going to get in a little bit closer. So yes, there's signs of corrosion around the tab, but that's not surprising because the conformal coating, which is that UV glue, didn't extend up to the tab, so the tab's been out in the rain. There's also corrosion around here. This is the transient suppression diode. Sits quite high on the board, and I don't think the conformal coating, the glue, had actually sealed that leg, so we're getting some sort of green copper related corrosion there. But the critical thing is that this still works because all the sensitive electronics, things like the analog to digital converter, where it's measuring the battery voltage, are sealed under this UV cured glue, and so this is working absolutely fine. In fact, I'm going to power it up. So I've got a 12 volt Maplin sealed lead acid battery here, which I'm going to use to power this up. Now I've got to be a bit careful because there's no protection diode in the yellow wire. That means if I plug red and black to the battery and touch these together, there will be the full current of the battery will flow through the Mosfet and it will destroy itself. So I'm just going to put a little baggie around the yellow plug here so that it can't touch the black one at that end. Now I can hook this up to this battery. Oh, which is pos and which is neg? That's neg. Will these just sit there? Probably not. Oh, they might do like that. And yeah, the blue light comes on. Now it should flash the battery voltage in a stylized form. Let's see what it does. 1, 2, that's 12 volts. And 5 or 6 flashes. So it's about 12.5, 12.6, which is what I'd expect on there. So this is working fine, even though there is corrosion on some of the, well, let's say less critical components. Now I've got 3 brand new very large lead acid batteries outside, generously donated by Jim, so thanks again Jim. So I'm sort of in the process of building some more of these PWM5 solar charge controllers, but I've designed a new board for this. And I'll put links to my Easy EDA account or design library so that you can see what I've done with this. Essentially, what I've done is I've shortened it ever so slightly, although there is a compromise there. If I can find my Mosfet, yes, here it is. On this one, the Mosfet tab slightly extended over the edge of the board. On the new one, it extends even further. But theoretically, you could cut that tab off. I'm not sure it'd be a brilliant idea because there'd be a lot of vibration into the chip. But yeah, you could Dremel that off, I suppose. It's not needed because this is designed to work without a heatsink. So as I say, I've made the board ever so slightly smaller. And most importantly, I've moved the LED, which on here, because it's on the bottom, is actually under these wires. I just got that completely wrong. So on the latest version of this, I've moved the LED to the top side, on the same side as where the chip is. So with the wires underneath, you'll have unobscured view of the blue LED on the top. Now I'm going to design a new version of the PWM5, and it's kind of going back to the older days of through-hole components. In fact, I'm going to call it the PWM5 ThruHole. At least one person has said to me, I'd like to build a PWM5, but I don't really want to bother with all these teeny tiny surface mount components, which are incredibly fiddly. So yeah, I'm going to build a through-hole version of this, a bit like the old design. In fact, let's go through all the original designs. This is actually the very first prototype. It's on Veriboard, of course, and it was laid out in a sort of linear form with the Mosfet stuck up on the end. And in fact, I stuck with this idea of connecting wires to directly to the legs of the Mosfet so that there are no high current tracks required on the circuit board. I had that right from the very beginning. So that was my first prototype. Then I built two of the sort of square form factor Vero board, and these again are prototypes. There are various wires sticking up here so that I had scope points for measuring the pulse width modulation signal. There's actually a switch on here which connects to the only pin that I never ended up using in the end. But initially, in fact, let's just have a quick look at the schematic. It's this one. It's actually called M clear, and you can use it as a master clear or a reset line to the microcontroller, but you can also reconfigure it via the fuses to be a general purpose digital input. And I had it for a while reading this switch so that I could press the switch to switch between different software routines to sort of see how they were working. This one also has the Mosfet gate resistor is plugged into a little 2-pin socket, so I could experiment with different gate resistor values. Where's that on the schematic? Yes, it's this resistor here. Now it seems like a very high value, but it's highly effective in reducing EMI, electromagnetic interference, emissions from this device. The EMI emissions from this are very low. So then I started making production units, and this was when I was selling them on eBay and through my website. This one is clearly a Vero board unit. You can see the Vero board holes there. And then I had a printed circuit board made. Now I don't have the design files for this because they were done in some archaic PCB package. I think it was Easy PC. I think it was that, but I didn't really know what I was doing, and the design files were a total mess. Which is why I want to redesign this, probably slightly different form factor, not quite a square, maybe slightly longer and narrower, not quite the gum stick form factor. These of course have got water in, and so they're useless. They're also covered in water because it's raining outside. Now there's something rather remarkable out here. This is my battery bank. It's 6 gel lead acid batteries, which I use to run my projects in the workshop. It's charged, well, was charged by these 3 charge controllers. Now the 2 on the left have long since failed, but that third one's still going, and that's been there for I don't know how long, 6, 7, 8 years, and hasn't yet failed. It's still working. Amazing. Here is the very last panel with those printed circuit boards. They're single-sided, and in fact if I flip it over you can see on the back that what this was essentially, there are a couple of surface mount components on here actually, 1 or 2, not many. That one's even the right way up. I kind of copied the Vero board layout to some extent, so quite a lot of this PCB just looks like Vero board because I didn't really want to do a complete redesign. Yeah, 1 or 2 of the tracks which were wire links on the Vero board version became tracks on this version, but yeah, essentially this was just the Vero board version committed to a printed circuit board. That web address is no longer active because my server is not now functioning. So this ThruHole version of the PWM5, I'm kind of thinking it might be around this sort of size, might be slightly larger, this sort of rectangular form factor. The Mosfet is probably going to sit, I can't get the legs in because there are no suitable holes, but it's probably going to sit like that and then have components running down both sides and a big space here. It's going to be, well, single-sided in the sense that components will be on one side, but it'll be a double-sided board, and that'll allow me to create a new layout that kind of works. I'm also going to put holes in the corners for attaching the 4 wires, the red, the yellow and the 2 blacks, because some people I know don't like the idea of soldering wires directly to the legs of the Mosfet, so it'll have that. But what I also want to do is put a programming header on there so that the PitKit programmer can be just plugged in and the code can be written to the chip with this as a target board. And that's because I do want to make some changes to the code. So when I was manufacturing these things, I did have some problems. They were minor problems, but these things varied in accuracy. So whereas one would float the battery voltage at, say, 13.5 volts, another one might do it at 13.4, and then the next one might be 13.6. And I did wonder initially whether it was these resistors, but actually they're very precise these days. It ended up being this regulator, because of course the voltage coming into an analog to digital converter is with reference to a reference voltage. Now very often that's VDD, and that's how it works in this case. So if the regulator was providing exactly 5 volts, then the float voltage of the battery would float at exactly 13.5 volts because of this ratio and the set point that's in the code. Regulators that weren't quite 5 volts, if one was say 4.9 volts or 5.1 volts, then the battery voltage, the float voltage of the battery, in other words the voltage that the microcontroller is trying to get the battery to, would vary because the reference voltage was varying. And so I wanted to implement some software which would be a calibration process. And I thought I could do it with this reset line because it's not connected, it's not used in the final production unit. And I thought what I could do is I could just briefly short this to ground, reset the CPU. Now the CPU, or the microcontroller, can work out whether it was reset with a master clear reset or whether it was reset by simply having power removed. It knows the difference. It has little flags that you can interrogate and see. And I thought what I could do is if you reset it this way, it would simply step through a series of calibration values and recalibrate the unit to get this 13.5 float voltage exactly right. But I never implemented it. I kind of implemented bits of it or tested the code for it, but I never put it in the unit. Well, now, since going to the surface mount version, and I'm using a different regulator, this is the HT7550, this thing has a 3% tolerance. The LP2950 had a 1% tolerance. So the ThruHole versions varied a bit. These are going to vary wildly. So the calibration process is needed more than ever now that I've got this less accurate regulator. The tolerance is higher on this regulator. It can be, I think, down to about 4.7 volts or 5.3. It's quite a wide range of tolerance, whereas this one was much more accurate. So the calibration software is actually much more important now, and I do want to implement it. So just getting back to PWM5 variants again, after I stopped manufacturing the PWM5 and I started making printed circuit boards using JLC PCB, I came up with this gumstick version. Let's just get in closer on that. And this was a sort of curious hybrid of quite a few surface mount components, only on one side of the board. But I kept the through-hole capacitors, and I also kept the regulator, which is this 3-terminal device here. So of course this has the more precise voltage regulation. And then I committed to a full surface mount version, which is this tiny PWM5 Femto. Now, out of all those versions, I want to end up with just 2, a very tiny Femto-sized all surface mount, double-sided because there are components on the other side as well, miniature surface mount version, and then this new through-hole version. This, of course, isn't anything, it's just an idea of the size, which is going to be all the original through-hole components, but in a nice, neat layout and with additional features. Those will end up being the 2 versions of the PWM5, which I will sort of actively remain interested in. Now, if you're interested in the Solar Charge Controller, the PWM5, you may have watched a series of videos, I'll link to the first one up there, called Secrets of the PWM5. What that was a series of videos where after I stopped manufacturing it, and therefore there were no commercial secrets as it were, I kind of let everyone into a whole range of topics about problems I had. And one of them, of course, was tolerance and inaccuracy in that voltage regulator. But something I never mentioned in that series, and I just want to tie up that loose end, was I wanted to talk about these 2 resistors, which are a potential divider from the battery down to the analog to digital input on the microcontroller. And we've got 82K here and 20K. And although those values don't seem anything special, they are actually very special. And I'll try and explain why. So the firmware for the PWM5 is written in assembly language, and that means that you're writing in near machine code. One thing you certainly don't have is maths libraries or math libraries. There's no fancy conversion routines or scaling routines. Everything has to be done effectively in binary. So I thought to myself, what I really want is a way to get the voltage on the battery to come in to the microcontroller as something which doesn't require much conversion in order for me to display that flashing blue LED and display the voltage in its decimal form. So what I came up with is these two resistor values, and I'll do some calculations to show why these are very, very helpful values. So let's first calculate the voltage on the battery, which will result in the maximum 5 volts going into the analog to digital converter. So the voltage on the battery, let's call it X, over 5. So the ratio of the battery voltage to the maximum ADC voltage is going to be this ratio. It's going to be the maximum resistor value, which is 82K plus 20K, so it's 102K. Let's just call it 102, over the proportion that the analog to digital converter can see, which is this 20K. It's just a potential divider. So it's 102 over 20. So I'm just going to rearrange this. X equals 102 times 5 over 20. Let's work that out. Now, just before I work that out, let's imagine that this has an 8-bit A to D converter. In fact, it has a 10-bit, but we'll make it an 8-bit just to make stuff simple for the moment. So the maximum value we can have in binary, given 5 volts on the ADC line, will be 255. So let's work this out. It's 102 times 5 equals 510 divided by 20, 25.5. So the voltage on the battery that would give rise to 5 volts coming into the ADC is 25.5 volts. Now that will give us a binary value, assuming this is an 8-bit ADC, of 255. Now, do you see the convenience of having this resistor value combination? What we get is 25.5 volts on the battery gives us 255 in the A to D converter's result byte. So you can see how useful this is. If the battery is, say, fully charged and the microcontroller is maintaining it at 13.5 volts, then the value or the voltage coming in here, I can calculate it if you want, but it doesn't really matter. The conversion of that voltage to binary in the A to D converter will give the decimal value 135. 13.5 volts on the battery will give 135 in decimal. Of course, it's a binary register, but 135 will be the decimal value in that register. It makes the maths so much simpler. Now, actually, this PIC microcontroller has a 10-bit A to D, so in fact, the resolution of the voltage measurement, instead of being a tenth of a volt per bit, it's actually a 40th of a volt, because we've got 4 bits for each of these tenth of a volt increments. So once you've read in the value on the ADC pin into the ADC result register, that of course is in binary. Then you have to get that binary value converted to decimal, and I've just looked at the code. Now it's a little bit difficult to follow, and I don't remember this terribly well. It's a long time since I worked on this. There's also this Zener voltage. The original circuit diagram had a Zener diode, but it proved to be far too temperature sensitive, so I took it out. But the code retained a sort of notional Zener diode. Don't ask me about that. But anyway, this routine does a bunch of setup stuff, and then it does a conversion to decimal using repeated subtraction. So in this case, I'm adding F6, which is a high number, which does the equivalent of subtracting decimal 10. It goes around the loop as many times as it can until it underflows. That then gives you a result of all the whole volts, and the tenths remain. Add a whole volt back, and then the tenths go into a separate register. So what you end up with is two memory locations which hold the number of volts in one memory location and the number of tenths of a volt in another memory location. And then it's possible to send that out to the flashing LED, which is this thing here, and flash it in a way that you can see the battery voltage as a decimal number. Now, just going back to this for a moment, these production units, which after a few years, the seal between the heat shrink and the hot glue, which I poured into the end, started to break down, and that's why the water started to move in via capillary action. And this one that is still working fine that I keep outside, what I want is a combination of these two things. So I'd like to conformally coat the PCB so that the sensitive electronics is completely protected. Then I will encapsulate this in heat shrink, much as I did these, pour hot glue into both ends. That provides most of the weather seal. So this new unit, and indeed the PWM5 ThruHole, when I design a PCB for it, will have a sort of double protection against the elements, conformal UV glue coating, and then an outside casing with hot glue seals at either end. And that should give it, I would say, at least 5 years in the field, probably more actually with the conformal coating. Might last forever. Now, of course, these don't look very pretty, but the final production units that I was manufacturing had an outer piece of heat shrink, black. There's no seal on the ends. It relied on the seal on the clear heat shrink. The clear heat shrink is just inside there. In fact, you can see it poking through that hole. It had a label, and so it actually looked quite respectable. So that's the future direction for the PWM5 Solar Charge Controller, the ultra tiny Femto in a little piece of heat shrink and suitably weatherproofed, and a new design which I'm going to start laying out, which will be the PWM5 ThruHole. There will be two versions. Cheerio.